Today's topic, we are looking at the last section in Unit 3, which is on something called L'Hopital's rule. So not hospital, not L'Hopital. We pronounce that L'Hopital. So this is a rule named after a mathematician, L'Hopital, who discovered a special relationship between the limit of a function and the limit of the derivative of parts of that function. So the goal for this, guys, we're actually going to learn a new way to evaluate a limit that we haven't seen before. And up until this point, if we wanted to evaluate the limits of these functions, we would have to use other non-calculus methods that can be sometimes time-consuming, or other times there are no algebraic techniques that we can use to actually evaluate the limit. So we would have to resort to using a calculator to graph the function or look at a table of values, when now that is no longer necessary. L'Hopital's will work for just about all of those other scenarios. There are certain criteria that have to be met, but we can use this for most of these other problems that we couldn't tackle before. So before we dive into the new stuff, we're going to take a look and review some of the older problems that it's probably been a while since we've tried any of these. So we're going to go back a little ways, back towards the beginning of the course with our limit stuff. So remember, the purpose of evaluating a limit is we're not concerned with what the value of the function is at a value of x, but rather what the value of the function is approaching from both the left and the right side. So we had a flow chart to help us help guide our thought process when evaluating limits. And the beginning of that flow chart is always using direct substitution. Remember, the idea is if the function is well behaved at the value of x that we're concerned about, in this case, x equals 4, if there aren't any holes or asymptotes or jumps or breaks or any crazy stuff like that at that value of x, well, then we can just simply plug it in and the value of the function is the limit. But we don't know that until we actually use that direct substitution method. So we're going to plug 4 in and then evaluate the answer and analyze, see where that puts us. So if I do that, substitute 4 in, I get 4 squared is 16, minus 4, minus 12. And then in the denominator, 4 squared is 16, minus 16. So when I clean all that up, I end up with 0 over 0. Well, if you remember back to Unit 1 at the beginning of the course, this is where we learned about the indeterminate form and the idea that this is not an answer to the problem, but rather a red flag that should be triggering something in your brains to tell you there is hidden information in this problem. There's something about the current form of the function that is hiding the real value of this limit. So we have to do some work to rewrite this to try and help us figure out what that actual limit is. So because these are both polynomials, one of those methods was factoring. So in this case, the numerator would factor to be x minus 4, x plus 3. And I don't think I said at the beginning, if you guys are using my guided notes, the 2 and the 6 did not copy when I printed this to a PDF, so please put those in there on your paper so you guys see the right values. And then the denominator factors to be x minus 4, x plus 4. So now we see a common factor. And again, that was a pretty common thing with these rational functions with polynomials on top and bottom. What is creating that 0 over 0 is a factor that corresponds with the value of x that we are approaching the limit at. As long as there is that factor in there, it's going to make both the top and bottom equal to 0. So because it's a common factor, we just simply reduce that out. In doing so, that just created a hole on the graph at x equals 4, because this is still a restricted value for the original function, so we can't use it, but I just eliminated it, and now the rest of the function works. So now I can take the limit of the result. So the limit is x approaches 4 of x plus 3 over x plus 4. And again, after we fix it, now we just try direct substitution again. So in this case, I would get 7 over 8 or 7/8 for that limit. That's it. So that was a quick review of the factoring technique to try and rewrite. So again, that wasn't the only one. We also had the trick with radicals where we multiply top and bottom by the conjugate of whatever the denominator is. That helps fix whatever the numerator's conjugate is. That helps us get rid of the radicals and then be able to take the limit. We also have some trig stuff that we're going to look at here in a second, all kinds of different methods that we can try to fix it. But the key is when that indeterminate pops up, that's when we know that something's going on and we need to fix it. All right, now for the second one. This one, if you notice, this is a limit at infinity. So remember, limits at infinity are all about growth rates. This has a lot to do with horizontal asymptotes. So in this case, we're looking at a horizontal asymptote on the right side of the graph, or we're exploring to see if there is one. So we have shortcuts that we've talked about in the past, and those shortcuts will still be relevant to us and helpful. But L'Hopital's is really about doing all the legwork and proving, not just through the gimmicks and the tricks, why the limit is something, but a mathematical explanation for why it is that we get those results. Now, in the past, when we've talked about this, or these limits at infinity, we talk about growth rates. So in this case, both numerator and denominator are both quadratics, and so the extra terms cancel out. We're really just focused on these first two guys. And because they're the same degree, we would take the ratio of those coefficients, those leading coefficients, and that produces our limit. So we know from past experience that the limit of this function as x approaches infinity is 3/4. Now, for what we're going to do today, it's going to be important for us to highlight some information about this guy. So one of the properties of limits says that the limit as x approaches c of a over b is equal to the limit as x approaches c of my top function divided by the limit as x approaches c of my bottom function, as long as that bottom limit is not 0. Again, that would be, because of the fractions, that would be a no-no. But in this case, what we essentially could do is we could take the limit of the top and the bottom function independently. And that's a really big key for us in L'Hopital's process. So I wanted to hit on that property again, because again, it's been a little while. Now, had we tried to do that with this function, limit of this numerator, this quadratic, well, this is a quadratic function that opens up because a is positive. So on the right side, that guy is going to positive infinity. The bottom guy is also a concave up quadratic function, so its right side is also going to positive infinity. So what happens is this creates another indeterminate form. Most of the problems that we saw at the beginning of the year, the indeterminate form was always 0 over 0. But infinity over infinity is another type of indeterminate form because it's a ratio of quantities that don't really mean anything. So infinity just means the top gets infinitesimally large, so does the bottom. So just knowing that both keep getting bigger and bigger doesn't really tell us the whole picture. So this, again, is a clue that we could do something to the original form of this guy. Now, that thing that we're going to do is what we're going to learn today. That's the L'Hopital's. In the past, we would just simply revert back to our growth rate rules, same over same, so it's the ratio of those coefficients. But again, today we're going to dive in a little bit deeper to this kind of problem. But we still do know in the back of our mind those growth rates still work, so we do have 3/4 for our limit. All right, now for the third one. Not a limit at infinity, so this time t is going to approach pi over 2. And again, I've got trig functions, that's why we got pi's mixed in here. But we should always still try our direct substitution first. So pi over 2, again, that is on our unit circle, that is up top. Coordinates there, x is 0, y is 1. So sine of pi over 2. Now remember, when we see sine squared, the order of operations, remember, that is really sine of t quantity squared. So that means I'm really plugging pi over 2 in, evaluating the sine of that angle, getting an answer, and then squaring it. So if I do that, pi over 2, the y coordinate is 1. So 1 squared is 1. So I end up with 1 minus 1 on top. And then on bottom, I would have pi over 2 for that t value times the cosine of pi over t, cosine of pi over 2 would be 0. So we actually end up with another indeterminate form. So this is one where we are left trying to do manipulations using our trig identities. So hopefully this whole time that this problem has been on the screen, this 1 minus sine squared expression has kind of been dinging some bells in your head That is our Pythagorean identity. If I take sine squared plus cosine squared equals 1, remember that's the one form to rule them all. That's the one we start with. And if I move the sine squared term over, I get cosine squared equals 1 minus sine squared. So this entire numerator is equivalent to cosine squared t. Well, why is that helpful? Well, now I have a common factor of cosine of t in the numerator. And again, that cosine squared, that squared part there, that really means, again, it's written out like this. So it's the cosine of t function squared. So there's two factors of it in the numerator. So I can cancel one factor out with the one factor on bottom, and that leaves me left trying to take the limit as t approaches pi over 2 of cosine of t over t. So when I substitute that in, cosine of pi over 2 is 0. T on bottom is pi over 2. So 0 divided by any non-zero number is automatically 0. So I don't need to worry about flipping anything or anything crazy like that. So that is our limit. Have to use our trig identities. Okay. And now this last one. So limit as h approaches 0 of cosine of x plus h minus cosine of x all over h. Well, if I try direct substitution, I get cosine of x plus 0, which is just cosine of x, minus itself, so that's 0. And then h on bottom becomes 0. So again, a red flag. But this one is different. So even though you can start all these limit problems off with direct substitution, when this one gets to that red flag stage, you should be thinking to yourself or recognizing on here that this is not a typical function that we would evaluate the limit of. This has a special structure to it, a special format to this expression. This is the limit definition of our derivative function. So you have to be on the lookout for these. So this is a kind of a trick question. This is another way of saying my original function is cosine of x, and I want to know what is f prime of x equal to. Well, the answer to that is negative sine of x. We know that from our derivative rules. But again, the limit definition says that f prime of x is equal to the limit as h, or remember, we can also use that delta x notation, but h is easier to work with, of f of x plus h minus f of x all over h. So if that is the form, if you go back and look at the original problem here, cosine of x plus h, that is the f of x plus h, especially now that I have identified our original function as cosine. I just substituted that x plus h in there and then subtracted the original function as well. So again, this is a special format, bit of a tricky question. So the answer to this guy, overall answer to this, is just simply negative sine of x. So we're not going to really do much work with these today because it doesn't really hold much weight with L'Hopital's, but just another reminder. Again, it's been a while since we've seen that limit definition. All right, so now I want us to think about think about the limit as x approaches 0 of e to the x minus 1 over sine of x. So in this case, if we can't figure out a way to simplify this, then we would have to use a table or graph to evaluate that limit. But again, as always, let's try direct substitution and see what we get. So if I tried to use direct substitution here, I would get e to the 0 is 1 minus 1 over sine of 0, which, again, angle of 0 is on the positive x-axis, so the y-coordinate there is 0. So that creates 0 over 0. So if that is our result here, hope things don't go crazy. Again, that is an indeterminate form. But the other problems above that we got an indeterminate form for all had algebraic ways of us manipulating the original function. So in this case, though, there's no common factors in top and bottom that I can cancel out. E to the x has no identities to equate it to sine of x. So without knowing even more calculus that is way down at the end in calculus 2, there's no other way for us to rewrite this expression or this relationship here. So because of that, that's why this is saying the only other option here would be trying to use a table or a graph to evaluate the limit. Well, if you have that capability, then you would never want to do it by hand because it's way easier just to use a table or a computer to generate the table or graph. So instead of doing that, we are going to learn how to use L'Hopital's rule. L'Hopital's rule can solve this in a very easy way. It's actually way faster than using technology because it would take longer to type this into a table and generate all the values than it would be to apply L'Hopital's rule. So let's dive into our new rule here. So L'Hopital's rule. Definition says we're going to let f and g be functions that are differentiable. Remember, differentiable just means that they have slope, they have a rate of change that we can calculate, and that can be calculated using the derivative function. So we're going to say that they're differentiable on an open interval a to b with c, except possibly at c. So that c is just some value actually in the given interval. Okay? So what L'Hopital's rule says is if the limit as x approaches c of a function f of x over another function g of x, so really we're taking the limit of a rational function, but we're going to separate the numerator and denominator of that function into two separate quantities, two separate function rules. So if we take the limit of their ratio and we get 0 over 0, so that indeterminate form, then L'Hopital says that the limit of the original ratio will actually be equal to the limit of the ratio of their independent derivatives. So notice that we did not treat this like a quotient rule. We didn't go from f of g of x and turn it into the derivative of that quotient using the quotient rule. This goes back to the property of limits that I mentioned at the beginning of the video. We're treating each part of that fraction or that rational function as their own independent function, and therefore we're going to take the derivative of the top and the derivative of the bottom separately. So if I were to take the limit of that new ratio, whatever that answer is, that is actually going to turn into or be equivalent to the limit of the original function. So this has to do with the special relationship with how the y values for f and g of x compare to one another when we find their ratio, and the idea that their ratio of y values is equal to or related to the ratio of the slopes. So as the y values of f are increasing, they're going to get bigger and bigger. Y values of g increases or decreases, they're going to get bigger or smaller. And so that has a direct correlation to the value of the derivatives for f and g. So this is a special, easy relationship to apply. This is really a nice, easy way to evaluate some pretty difficult limits that otherwise, again, we'd have to use some kind of technology. Now, most of the time, the indeterminate form that we're going to get for these is going to be this 0 over 0, but that's not the only indeterminate form that can be created. So other possible indeterminate forms, ratios of infinities. Doesn't really matter if one's positive or one's negative. Any kind of infinity over any other kind of infinity is another indeterminate form because it just is describing an increase or decrease without bound. And so it's impossible for us to know how those two quantities actually ratio out to, and compare to one another. Other forms, a type of infinity adding or subtracting to another infinity, also an indeterminate form. The 0 times infinity. This one's kind of unique because really 0 is another way of saying 1 over infinity. So it's like another way of representing an infinitesimally small value. So if we think about the quantity of 0, that can be rephrased as 1 over infinity. So this really just reverts back to that infinity over infinity form. So we're going to take a look at a few different examples here, and each one's going to kind of walk us through different types of functions that can show up and different ways that these indeterminate forms can pop up from one problem to the next. So for this first one, we're actually going to go back to the last example here. Again, we know that this produced an indeterminate form. We've seen that already. We got 0 over 0. So how we would write this, There's not really any magical notation to show that we're applying L'Hopital's rule. We really want to, if we're doing this accurately, we'd really want to say that the limit as x approaches 0 of our original function equals, so we basically want to rewrite the original notation, and then we're going to show that it is equivalent to the result of L'Hopital's. So we're still taking the limit as x approaches 0, but now we're going to take the derivative of the numerator and the denominator, again, totally separately of each other. So if we do that, derivative of the top would be just e to the x. Again, that minus 1 is really going to just disappear. It's a constant. And then the denominator will now turn into cosine of x. So again, after each iteration, so there are some of these problems where you have to continue to apply L'Hopital's over and over and over again. Because if we think about the definition here, if the limit of f over g is equal to the limit of f prime over g prime, then it would follow that the limit as x approaches c of f prime over g prime would be equal to the limit of f double prime over g double prime, because it's the same relationship between f and f prime as it is between f prime and f double prime. It's really just different names of different functions. So that continual relationship, it can go on forever and ever and ever as long as the original functions don't eventually terminate. So for a function like e to the x, looks like it's doing that disappearing thing again. For a function like e to the x or trig functions, there's an infinite number of derivatives that can be found because e to the x will remain e to the x forever, and then the trig functions, sine and cosine, just bounce back and forth between one another. So there are some of these L'Hopital problems where we actually have to continue to take derivative over and over and over again. As long as the direct substitution process of this result produces an indeterminate form, we can continue to go through this over and over again. But it's very important that you are looking for an actual indeterminate form. Remember that 1 over infinity and 1 over 0, those are not indeterminate forms. Those are actually final answers to these problems, okay? Now, sorry, back to this one. So if I try direct substitution now, I get e to the 0 over cosine of 0. Whoops, not theta. Sorry, bad habit. Cosine of 0, e to the 0 is just 1, and then cosine of 0 is also 1. So we don't get an indeterminate form here, which means we are finished with this problem, and our final answer is just 1. Now, if I had a graphing calculator like Desmos, then I could graph this guy super quick. So e to the x, minus 1 over sine of x. And now if I look at the limit as x approaches 0, if I try to get the point on here, you guys can see that is actually a hole. That function is undefined at x equals 0. And again, anytime that we take a limit and get an indeterminate form at a value of x, but then later on find an actual value for the limit, that is describing a removable discontinuity or a hole on that graph at that value of x. And we can see that hole is, in fact, at x equals 0, y equals 1. So we kind of confirmed it with that technology. But again, we don't need the technology anymore because we have L'Hopital's. All right, let's take a look at a few more examples here. So next one. Now, this is actually the very first problem at the beginning of this section of notes. Again, we know the answer to this guy from earlier. We already did this problem, but I want to show you how much easier this is with L'Hopital's and how much faster we can get to that. Now, again, this all revolves around first getting that indeterminate result. So we know that when we substitute 4 in here, we're going to get 0 over 0. So if that's our result, now we're allowed to do L'Hopital's. So because now we know L'Hopital's is an option, you guys don't need to necessarily write down right after this notation that we get 0 over 0, because then it's going to force you to have to rewrite this whole thing again. I'm okay if you want to do some scratch work off to the side, but you still do want to make sure that you're at least testing to see if we get that indeterminate result. Because what you don't want to do is execute L'Hopital's rule if it was not necessary. Then you will not be getting an accurate result here. This special relationship is true if that indeterminate form is achieved first. That's why that was a condition here. So it's not that this relationship is always true. It's if the original limit is indeterminate to begin with, then this relationship holds true. So please make sure that you check that first. Now, the reason why I don't want to write it after this is now I can go right into setting up the first step or the first iteration of L'Hopital's. So derivative of my numerator is 2x minus 1. And then derivative of my denominator is simply 2x. So again, after every time you carry out L'Hopital's and you take derivative of top and bottom, try direct substitution again. And in this case, I get 4, if I substitute 4 in, I get 2 times 4 is 8 minus 1 is 7 over 2 times 4 is 8. And that is the exact same answer that we got earlier, but you can see how much faster and easier this was to get to that final answer than having to worry about factoring, reducing, and then rewriting and reevaluating. So very short and sweet, some of these L'Hopital rules problems. Okay, let's try this next one. Again, let's check for indeterminate first. So if I plug cosine or pi into x everywhere, in the top, cosine of pi would be -1. If I multiply this by 2, sine of 2 pi would be 0. And then plus 1 would be plus 1, obviously. So those produce 0 in the numerator. And then pi squared minus pi squared will also be 0 over 0. So we do, in fact, have that red flag, that indeterminate form. So now we can take our derivative. So the derivative up top would give me, let's get our limit notation. So limit x going to pi still, that part never changes. But up top, cosine would turn into negative sine of x. Now for sine of 2x, that's really a sine of u, where u is 2x, so u prime is 2. So derivative of sine of u is cosine of u times u prime. So this will really turn into plus 2 cosine of 2x. And then the constant will drop out. And then on bottom, x squared is just going to be 2x. Pi squared is just a constant, so a number, so it also simply drops out. Now we can try our direct substitution. So when I plug pi in, again, negative sine of pi, well, sine of pi is 0. And then cosine of 2 pi is 1. So I got 2 plus 1 there, or 2. And then on bottom, that would just be 2 pi. So my final answer here would be 2 over 2 pi, or simply 1 over pi. That looks like a crisscross something. And it did the same darn thing. It's annoying. All right, there we go. That was way too difficult. So again, this is a very straightforward, repetitive process sometimes, but you do always want to double check that after you've done L'Hopital's that we do in fact get a finite answer. So just be on the lookout. Make sure that if you were to get another set of indeterminate form values, then we would have to continue that process over and over again. All right, so let's try this third one here. So limit as x approaches 1 of sine of pi of x. So if I plug 1 in, I would get sine of pi, which is 0. And then on bottom, I would get 1 squared is 1, minus 2 times 1 is 2, plus 1. So that is also 0. So we do get an indeterminate. So now we should be taking the derivative of top and bottom. So sine of pi x, well, I already have the u set up here, so I'm just going to change my u's out. Instead of 2x, it's just pi x. So instead of 2 cosine of 2x. This is just going to result in pi cosine of pi x. And then on bottom, we just have that polynomial, so we get 2x minus 2. All right, so now we try direct substitution again. So plugging 1 in, that would give me pi times cosine at pi. 1 pi would just be negative 1. And then on bottom, we would get 2 times 1 is 2, minus 2 is 0. So this could be a situation where someone misinterprets this result, sees that 0 on bottom, and just automatically thinks, okay, it's indeterminate, so I got to do L'Hopital's again. If you continue to do L'Hopital's past where it's correct to do it, you will get wrong answers. Because again, in this case, my final result is negative pi over 0. And again, remember that 0 represents smaller and smaller quantities being divided into negative pi. And when you divide by smaller and smaller quantities, you actually make it larger. So in this case, a larger negative value would mean this limit is heading towards negative infinity. That is our final answer. So again, final answers can take on the form of a non-zero number over a non-zero number, a non-zero number over 0, which is a form of an infinity, or a non-zero number over an infinity, which is really, again, a form of 0. So if you get any of those three, you're done. We don't have to just keep doing L'Hopital's until we get a traditional numeric answer. So some people get confused about this process. We're not always working towards just a number. Sometimes we are working towards other final results. So it's only if we get indeterminates that we will continue this process. Now we're going to take a look at how we apply L'Hopital's with limits at infinity. If you notice the first few examples there, they were all as x approached finite values, 4, pi over 2, whatever they were. But when we do these limits at infinity, we can still apply L'Hopital as long as we get our indeterminate form. But with infinities, it's much more likely that the indeterminate form is a ratio of infinities. That doesn't mean it's impossible for us to get an indeterminate form of 0 over 0, but it's much more common and likely to see the infinities mixed together, okay? Now, because of that, when we're doing these limits at infinity, you have to, we're going to approach these a slightly different way. So when we do our quote-unquote direct substitution process with this, you can't, infinity is not a number. We can't just substitute that into an equation, do the math, and get a number like we can by substituting 2 in. But that infinity symbol represents a process of if we were to substitute in larger and larger numbers, where are those outputs headed? So when we do this, you're going to see me write some notation that may not be traditionally acceptable to some people, but I feel like it still helps us remember what it is that we're trying to do and evaluate. So when I write this out for a direct substitution, I would be writing it out kind of in a similar fashion. I would think of natural log of infinity over infinity for x. Now, the bottom one is pretty no-brainer. That x is just getting replaced, which means on the graph of the function y equals x, as x goes to infinity, so towards the right, the y values are going towards infinity. That when I write that out, that's what it means. So we're going to be using a graphical approach for just about all of these to try and evaluate these limits at infinity. So I've already done the bottom function. I know I went kind of out of order, but that's because this bottom guy is easier to interpret. Now for the top function, natural log of x, we do have to remember what some of these parent functions look like. So natural log of x is kind of the inverse of the exponential function. So vertical asymptote on the y-axis, and we slowly increase as we move to the right. So this guy does continue increasing forever towards infinity when I go to the right. It just does so at a very, very slow rate. So natural log of infinity really is heading towards infinity as well. So another red flag moment, that's an indeterminate form. So now we have to apply L'Hopital's. So when we do this, now we haven't seen one like this, but sometimes when I do these derivatives of the top and the bottom separately, the forms that we're left with can be simplified as an overall ratio. So it's okay to go ahead and simplify it before we go to do that next step, because these are still quantities that are interacting with each other through division. So when I do this, this limit is going to be equivalent to derivative of natural log of x for just up top is 1 over x, and then derivative of x is 1. So this is what I mean. I would never leave this expression in this form. Dividing something by 1 is really itself, so this guy really simplifies. Now, this isn't me doing L'Hopital's or any other math besides just algebraic simplification. So that is the expression that I will now take the limit of as x approaches infinity. So the limit of 1 over x as x approaches infinity, we can think of that as 1 over infinity, and we just talked about that is a form of 0. So that is the limit as natural log of x over x goes to infinity. Now, another approach here. Now, again, this is L'Hopital's. If this was a quiz question or a test question, then I'm specifically measuring, can you perform L'Hopital's and understand when it's necessary? This is what I would want to see. But in the back of our minds, I want you guys to be logical, critical thinkers. So another approach to this, anytime that we're dealing with these limits at infinity, is growth rate. How does the rate of growth for the top function compare to the rate of growth for the bottom function? Well, I have both of these graphed here. Let me graph y equals x on here as well. Looking at those two functions, it should be painfully clear which one grows faster. In this case, the numerator, natural log, is growing much slower than that bottom guy. Even though y equals x doesn't grow very quickly compared to other functions, compared to natural log, it grows much quicker. So because of that, we end up with a slow-growing function over a fast-growing function, which we've talked about in the past in terms of polynomials. If I had like x over x cubed, this would be a similar relationship. And in all those cases, that limit or that horizontal asymptote ended up being at y equals 0. Well, polynomials aren't the only kind of functions we can take the ratio of to create horizontal asymptotes. You can do it with any kind of rational function, as long as those growth rates follow that particular pattern of slow over fast or same over same. That's how we produce those horizontal asymptotes. So I do want you guys to still keep that in mind, because there are going to be some situations where, even though L'Hopital's applies, to actually solve it that way would take a very, very long time. And so sometimes we have to revert back to our basic logic and critical thinking skills. All right, let's try this next one now. So again, limit as x approaches infinity, we're going to identify the limits of each function individually, up top and bottom. So for the top guy, this is a quadratic function. We don't need to know all of the details about these functions. It's really just about end behavior, specifically whatever direction the infinity that we're working with applies to. So in this case, x goes to positive infinity means the right side of each of these graphs. So this is a quadratic function with a positive a value, so we know that it opens up. So on that right side, we know that that function is heading towards positive infinity. Then on bottom, 5 minus 4x squared, that would be another quadratic, but it has a negative a value. Even though it's not in standard form, that's still the highest degree terms coefficient that does all the work here. So this is a quadratic that would open down. So on the right side of it, we're going to negative infinity. So realistically, the signs of the infinities is not the important part here. It's the fact that it's infinity over infinity. That is what makes this indeterminate. So because of that, now we can apply L'Hopital's. So the original limit would be equivalent to the limit as x approaches infinity of the derivative of the top. So, oops, not 3. Derivative of 3x squared would be 6x. And then plus 7. And then derivative of the denominator, constant disappears. So this would just be negative 8x. So now we try L'Hopital's yet again. So now if we took the limit of the top function, now this is a linear function with a positive slope. So we know that it's going up and to the right. No matter what the slope is, it's going up. So on the right side, we are heading towards positive infinity again. And then on bottom, negative sloped line. So as we go to the right, we are going down towards negative infinity. Similar result. So again, because we got indeterminate form, we are allowed to do L'Hopital's a second time. And if you notice the structure here, this kind of relationship or process happens very, very often, or not often, always, when we have polynomial over polynomial. Because the end behavior of polynomials, the arrows, polynomials can't have horizontal asymptotes. So the only kinds of functions when we take these limits at infinities that can actually approach numeric values on top and bottom would be functions that have some kind of horizontal asymptote. That's why these relationships or ratios with the indeterminates of infinities, that's why those are so prevalent with these kinds of problems. So it's very rare for us to actually get numbers in here and not some kind of infinity. So because of that, L'Hopital's is used quite often. So every polynomial has a positive or negative infinity limit as x approaches infinity. So it's just going to continue this cycle over and over again. So it's when we are applying L'Hopital's with the limit at infinity to polynomials on top and bottom, it's very common for us to have to repeat the process several times. So how many times is actually going to correspond to the smallest degree of either top or bottom, because it's going to have to continue to wane down to a constant before we can stop. So in this case, both are quadratic, so we're actually going to have to do it twice, and that's why we're doing it one more time here. Once I've done or taken a second derivative of a quadratic, we know that we are going to be at a constant value, so it's impossible for us to get these infinities anymore. So the numerator now, its derivative would be 6, denominator would be -8. So the limit of a constant as x approaches any value is that constant. So we just get -6/8 again, or -3/4. Now, some might be looking at that and saying, why did we go through all of that when we have our shortcuts that explain or gets us to that answer of 3 over -4 way faster? Well, that's because the shortcut is a shortcut. Shortcuts never explain in detail or prove why things work. The shortcut is the shortcut because someone else did all the proof work and we know what the final result's going to be, so you're allowed to skip to get to that answer to be more efficient. But if I'm looking for the explanation, the mathematical proof or reasoning behind why that answer is the answer, that's what L'Hopital's is doing. Now, there are other techniques, algebraic techniques for a problem like this that can explain away why or how we can get -3/4. But L'Hopital's is a kind of all-encompassing process that we can use for just about every kind of problem. So that's why we choose to do this way rather than some of those other techniques. All right, let's keep pushing forward. Let's try another one. Now, for this one's kind of unique because when you look at it, this is the only problem on your paper that is not a fraction to begin with. So if I were to try and do this problem in the form that is given to me, I would plug t infinity into the t squared. So that would produce, if we think about the limit of the function t squared, which is just like x squared, just using a different input variable, as t or x goes to infinity, the right side is going to infinity. And then if I do the same for e to the -2t power, well, e to the t looks like this guy. E to the +2t is just this guy going twice as fast because I've created or squared that base. So because of that, it's still going to go to infinity. It's just going to do it a lot faster. E to the -2t, well, that is a horizontal reflection. Remember, when we change the sign of our input, we flip over that y-axis. So e to the -2t looks like this guy. So as t goes to infinity on this function, we're actually approaching a horizontal asymptote with a value of 0. So this is another type of indeterminate form. But earlier I mentioned to you guys that 0 can really be rethought of as 1 over infinity, which is helpful to us here to explore how we would actually get to apply L'Hopital's, because the definition of L'Hopital's requires this to be in fraction form so that I can take derivative of the top and derivative of the bottom. Well, seeing it as 1 over infinity may trigger something for you that when we have those negative exponents, that really means that that factor belongs in the denominator. So this is not me doing L'Hopital's. This is me just rewriting the original. I can rewrite the original in this form, t squared over e to the 2t. And now if I took the limit, I would get infinity over infinity, which is a more traditional indeterminate form. Doesn't really matter which way you do it. Both of these, all of these different ways of writing it, tell us the same thing. I have to take L'Hopital or apply L'Hopital's to this expression. So let's do that. So anytime that you start off with a product, odds are it's either going to work out to be a finite value and you're done, or excuse me, not a finite value, a final answer. So either a finite number, 0, or infinity, or you have to rewrite it into fraction form. So now that that's taken care of, now we can do L'Hopital. So I'm going to take the limit as t goes to infinity of derivative of t squared will be 2t. And then on bottom, this is e to the u, where u is 2t, and u prime is 2. So then I get e to the u times u prime, or 2e to the 2t. So now if I take my limit again, 2t, another polynomial. Again, that one is a linear, so as I go to the right forever, still going to infinity. And then the bottom guy, again, this is just the same e to the 2t again, but now it's multiplied by 2, so even faster growing, but it's still heading towards infinity. So you can see kind of the same relationship as what I was talking about with the last one. You see that it's another relationship where they're going to keep having these infinities. Polynomials are going to have infinities. Exponentials are going to have infinities. So we're going to have to keep going with L'Hopital's until one of them disappears. Now, there is a situation where we'll recognize that neither will disappear, and that's where we're going to have to revert back to a little bit of logic and reasoning to get to our answer. That's really the only time that L'Hopital's fails is when it gets it. We recognize it's going to go into an infinite loop of infinity after infinity after infinity. But in this case, you guys should be able to recognize if I were to do this one more time, that linear will devolve down into a constant. So let's do it one more time. So 2t will turn into 2. 2e to the 2t. Now, if I just repeat that process, that 2 is already out in front, so this will turn into 4e to the 2t. So now I have a constant over e to the 2t is still going to infinity. So 2 over infinity is, again, another form of 0. So that is our limit for this guy. So that means, again, with all these limits at infinity, anytime that it comes out to be a number, that's another way of describing that this original function has a horizontal asymptote. So if I were to look at the graph of x squared, let's reset this guy, x squared times e to the negative 2x, you guys can see here, without zooming in too much, that this guy is going down and approaching 0. You can see it's basically flat after x equals 4. It's really hard to tell a difference there. So that kind of backs up what L'Hopital's found for us. All right, so let's try one more here. So for this one's unique. There's a specific reason why I want to look at this one. It has to do with this radical. So if I were to take the limit as x approaches infinity of this numerator, now this is not a graph that everyone knows what the shape of it looks like. So it is unique, and this might actually be a good one to show you guys the graph of. So square root of x, let's start with that. So this is the OG square root graph. This is what you guys should remember, the general shape of square root of x, but that's with just x as the input. When I change it to x squared, you should notice something that looks familiar. That is actually the same as absolute value of x. And that's something that we don't always do a great job in the lower level classes talking about. The idea of square rooting x squared. Yes, we always talk about their inverse relationship and the idea that it is, they cancel each other out, so we're left with x. But square rooting x squared the value of that square root is going to be positive unless I denote that it's supposed to be negative on the outside. But since I didn't do that, the outputs have to always be positive. But when I go to plug in any kind of value of x inside, that square automatically makes it the value of x squared positive. And then when I square root it, there are no issues. So when I square root and cancel out that square value, we have to make sure that the result of that expression still allows for positive and negative values of x to produce a positive value. If these absolute value bars aren't here, then a negative value of x plugged in is not going to produce the correct thing. For example, let me write this down so you guys can understand what I'm saying. So if I had square root of x squared and I plugged in -4 and I square that, well, some people may look at this and think, well, it's just equal to x. But if I did that, then that would mean that the square root of -4 squared is equal to -4. But I did not denote that this is supposed to have positive and negative results. When I do this, I'm squaring -4 to make it positive 16 first. And without any kind of denotion out in front that I also need negative results, this can't be -4. It has to be +4. That is why we need the absolute value bars around that. And that's why graphically, without making any kind of note of anything different, the square root of x squared is actually the equivalent of absolute value of x. Now, when I make this +5, has an even weirder effect to that. Okay, notice it's no longer a sharp turn anymore. It's actually a smooth turn. And we actually lifted it up slightly. This is the square root of square root of 5 is 2.236. So has a weird little effect inside of here. Most people would think that there would be a horizontal shift, but that would only occur if it was inside of the squared part. So if it was like the parentheses around x plus 5 squared, then it would be a horizontal shift. So this is a unique looking graph. Okay. So I just wanted to give you guys a visualization of what this is going to look like. Now, seeing what the graph looks like, if I tried to evaluate this as x goes to infinity, you see that end behavior is also going to infinity. Now, was that absolutely necessary to know what the graph looks like to evaluate this? No. We could use a little bit of logic. As my value of x that's getting substituted in here gets bigger, the squared value gets bigger. Adding 5 to it makes it bigger. And so its square root is going to continue to get bigger and bigger as well. So we can also use a little bit of logic there too. But I do really like the graphical approach when thinking about these. So then for x plus 1 on bottom, another linear function. So as we go to the right, still going to infinity. So surprise, surprise, L'Hopital's. Now, this is where it's going to get a little tricky. So I don't even know what that says. That is really bad. The radical up top, it's never nice to take derivatives of radicals, but this one is a u to the 1/2. So let's set this up. My u is x squared plus 5. So then u prime is 2x. So then u to the 1/2, typical, we've done this 1,000 times already. 1/2 u to the -1/2 times u prime, or u prime over 2u to the 1/2. So now if we go and fill this in with our u stuff, only in the numerator, and again, that's the little weird part here, the top guy and the bottom functions, each of those get their derivatives independent of one another. So when we write out this guy, the numerator's derivative ends up being a fraction as well. So we get 2x up top, but the 2 on bottom is going to cancel out with that. So I'm just going to have x in the top over the square root of x squared plus 5. Actually, I want to get rid of this. So we get x squared plus 5 inside. So the top guy is taken care of. And now in the denominator, x plus 1 was the original bottom, so its derivative is just 1. So at this point, before you go to take a derivative, or excuse me, take the limit of this result for top and bottom and find their comparison, anytime that we end up with a fraction in the top or the fraction in the bottom, or possibly fractions in both, we want to simplify this total result as much as we possibly can before taking the limit again. So in this case, the denominator just turned into 1. So really, this is just going to leave us with the fraction of the numerator. So I'm just rewriting this. I'm not applying L'Hopital's a second time or anything yet. So I'm only looking at this guy. So now that we've cleaned it up and rewritten, now we can take the limit of this result. So again, it's a fraction, so we'll take the limit of the top and the bottom independently. So the limit of x as x goes to infinity, again, that's a linear function. Right side goes up to infinity. And then the square root of x squared plus 5, well, we just talked about all of that to evaluate the limit of this guy in the first problem. So we end up with infinity down there as well. So we get indeterminate form again, another red flag result. So we would apply L'Hopital's again. But at this point, I want to point something out to you guys. So let's say that we went to do L'Hopital's again. Okay, I'm going to start the process. And I guess really we could carry it all out because we have everything we need to know. So let's just go ahead and do it. So derivative of the top is just 1. And then on bottom, you have the same function that you had up top in the original problem. So we know what its derivative is. It's right here. So all that's really going to happen here is that guy is going to go in the denominator. But then when I go to clean this up and rewrite it and simplify it before taking the limit, I'm dividing by that fraction. So it's like I end up multiplying by its reciprocal. So this actually just turns right back into the original problem. Square root of x squared plus 5 over x. I'm sorry, not the exact same problem, but x and x plus 1, they behave exactly the same as x goes to infinity. So what this creates is an infinite loop. So earlier I mentioned there are some problems with L'Hopital's where you get into a cycle of an infinite loop where we could keep applying L'Hopital's because we get an indeterminate result, but it's never going to wane itself away to reach a final result. It's always going to continue to cycle back to another indeterminate form, another, on and on and on forever, infinitely. So as soon as we recognize this, that this is an infinite loop, we have to kind of abandon L'Hopital's, and we're going to have to revert back to some of our basic knowledge of functions. So this is a case where L'Hopital's fails because it's never going to yield a definitive result. So now we're left going back and just looking at the original function, and we're going to have to worry about growth rates. This is the only result. Without using calculators or Desmos or some kind of computer software to generate tables for us, we're just going to have to simply use what we know about growth rates. So remember that as x grows very large, any constants added to variable quantities don't really matter. Any lower degree variable quantities added to higher degree variable quantities don't really matter in the long run. So in this numerator function, really the only thing that matters to us is this x squared that's inside of that radical. So that means that this numerator really behaves like the quantity of x squared, or square root of x squared, which we already talked about, is essentially the absolute value of x. The bottom is a linear function. It's going to behave just like y equals x. Again, that value of plus 1 does not really play very much of a role. So if we consider that these guys essentially behave exactly the same way, on the right side, as x goes to infinity, absolute value of x and y equals x, they are identical functions. So because they're identical, they are growing at the exact same rate. So this is like a same over same problem, in which case we are going to take the ratio of these coefficients. So in the top, I would have square root of 1, which is 1, and then on the bottom, I also have 1. So these guys are actually approaching a value of 1. That is the limit of this function as x approaches 1. And I can see that now that we know the algebra, the explanation behind it. If I take this function x squared plus 5 and divide it by x plus 1, you guys can see here that it does in fact have a horizontal asymptote at y equals 1. In fact, this is kind of a weird one on the right side because the graph actually dips below and then it comes back up to that y equals 1 value, but it's still approaching that horizontal asymptote. So this is an oddball situation. Doesn't happen all the time. But a lot of times what you'll see happen to create these problems is you will have a radical function in either the top or the bottom, and then when I take the radical of the largest degree, it's equal to the denominator. So because of that, they kind of bounce back and forth. The derivative of one kind of simplifies or reduces or combines with the result of the radical's derivative, and it ends up creating a similar relationship between these two. So another example, we could actually make one up here pretty quickly. Let's say that I had x to the second power over the square root of x to the fourth plus 2. If I tried to take the limit as x approaches infinity, I get that indeterminate result, but then its first iteration of L'Hopital's would give me 2x over, this guy would turn into 4x cubed over 2 square roots of x to the fourth plus 2. And when I flip-flop this guy and simplify everything out, these 2's reduce. And when I flip everything, what I actually end up with is the exact reciprocal of the original guy. So it would, again, continue to proceed in that infinite loop process. So it's just one of those oddball scenarios that you guys want to be on the lookout for when you're trying these problems on your own. All right, so for this last section, we're just going to try a handful more of problems. If you feel like you really mastered and understood everything up to this point, then these may not be necessary. This is we're not going to really see much of anything new here. It's just some more applications, more practice problems with these L'Hopital rule ideas. So this is a mixture. Some are approaching C, some are approaching infinity. If you guys would like to try these 6 on your own, pause the video, try them, and then come back to check yourself. That would be a really good idea so you get some independent practice, but you can check with me. So feel free, use these to your advantage to get some more practice, or you can stop watching and practice in class. All right, so I'm going to go over this first one. So again, always make sure that you are actually testing with direct substitution, because it's not a guarantee that this is L'Hopital. So if you tried to do L'Hopital's immediately for this guy, then you would end up taking the limit as x approaches pi of cosine of x over 1, which gives you an answer of -1. But that's not the answer to this problem, because when I do direct substitution with the original form, I get sine of pi, which is 0, over pi. So this answer is actually 0. So again, here's an example where if you just assume that it's not going to work out and you go through the motions and do all this extra work, you're going to be wasting your time. So please make sure that you guys are actually trying direct substitution first. It's never just going to be an automatic thing here with, whoa, I zoomed in way too far, with always having to do L'Hopital's, okay? Now, for this one, if I try that direct substitution, sine of pi is 0 again, but then on bottom, pi minus pi is also 0. So this is a scenario where we actually do need to use L'Hopital's. So if I apply L'Hopital's, we get the result of limit as x approaches pi of derivative of the top is cosine of x, derivative of the bottom, x minus pi, that's still just 1, that constant of pi doesn't change it. So now when I try substituting it again, now we get -1 over 1, or -1 for that limit. So again, it's all about that first attempt with direct substitution. What do I get as a result there? All right. All right, next one. Again, trying direct substitution right off the bat. In this case, I get cosine of 0 is 1. And then again, that 1 has to be squared here because, again, the order of operations, evaluate cosine, then square the answer. So I get 1 squared is 1, minus 1 is 0. And then on bottom, e to the 3 times 0 power is really e to the 0, or 1. Minus 3 times 0 is 0. Minus 1, also 0 over 0. All right, so we did get our indeterminate. Now we apply L'Hopital's. So for the numerator, we would need to take the derivative using a chain rule. So cosine squared, that's really a u squared function where u is cosine of x. U prime then would be negative sine of x, and then that constant is just going to disappear. Again, that is not a part of the argument, so we don't need to worry about that. So u squared is going to turn into 2u times u prime. So for our numerator, we just end up with negative 2 cosine sine. It doesn't technically matter what order we write those functions in. Some people prefer always writing sines first. I am one of those people, but it doesn't really matter which one goes first, because again, it's just a product. So that's our numerator derivative. And now for the bottom, e to the 3x, that is really an e to the u, where u is 3x. U prime then would be 3. So this is going to turn into an e to the u times u prime. So we get 3e to the 3x. Derivative of negative 3x is just negative 3, and the constant disappears. So now we can try our derivative again. So in this case, or excuse me, our limit again. So when I substitute 0 in, I'm going to get negative 2. Cosine of 0 was 1. Sine of 0, though, is 0. So that whole numerator is going to be 0. So as long as we don't get 0 on the bottom, we're done. But in this case, we will actually get 0 again because e to the 0 is 1. So we end up with 3 minus 3 again. Now you may be thinking to yourself now, oh crap, this is an infinite loop again. But if you look at the pieces that we have here, the only way an infinite loop occurs is if all of the functions in the original form do not dissipate down, or there's an infinite number of derivatives of all the terms. Well, if you look back at the original, trig will have an infinite number of derivatives. We can never stop taking derivatives of trig functions because there's always an answer to that. Again, the ones that kind of wane themselves away are the polynomials because of the power rule. So as long as it's a positive whole number power that you're starting with, there is a stopping point. So because of these two, again, the constant's always going to disappear, but this guy in particular, that's what's causing the 0. So the first one, the constant caused it, but that disappeared. But in the second round, that middle term's derivative is what caused the 0. So when I go to do L'Hopital's a second time now, that constant's going to disappear. So we should get a final answer this go-around. Now, what stinks is I have to do a product rule in our numerator. So unfortunately, can't avoid that. But it's not that bad. Negative 2 cosine turns into positive 2 sine of x. Then sine of x turns into cosine. So our derivative for the numerator turns into, again, insides plus outsides, turns into 2 sine squared x minus 2 cosine squared x. Yeah, there are things to do to that, but I don't need to worry about doing anything because I'm just going to plug 0 in anyways. But now for the bottom, we're going to repeat this e to the u prime, but there's already a 3, so this is just going to become 9e to the 3x, and again, that constant term now is gone, and we're just left with the exponential term. So because of that, we know for sure you will not end up with 0 in this denominator. You can have 0 up top, it doesn't matter. You could have a final answer or indeterminate. But if you know for sure your bottom is not 0, then you know that we're going to end up being finished after this round. So let's go ahead and evaluate direct substitution. Sine of 0 is 0, so I don't care anything after that. Minus 2 times cosine of 0 is 1. 1 squared is 1. And now on bottom, I get 9 times e to the 0, which is 1. So our final answer here is negative 2/9. So again, we don't want to assume anything. We always have to react to the results that we get. Don't get into the habit of making assumptions that could lead us astray. All right, let's take a look at this next one. So we've got limit as x approaches 0, 7x minus sine of x. So up top, that would be 0 minus 0, so 0. And then on bottom, we've got x squared plus sine of 3x, which is also 0 plus 0, so indeterminate form. Now, again, if we kind of do some pre-planning here, we should be able to realize something that's going to end up happening here. So these two functions our polynomial terms, 7x, x squared. If we had to keep going with our L'Hopital's over and over and over again, those guys will disappear eventually, and we may be able to take this result and simplify it. So we shouldn't have to worry about an infinite loop in this case, okay? So let's try L'Hopital's once, see what we get. Again, we don't want to make assumptions until we see the results. Derivative of the top is 7 minus cosine of x. And then on bottom, we would get 2x plus, this is a sine of u. Derivative sine of u is cosine of u times u prime. U is 3x, so u prime would be 3. So we get 3 cosine of 3x. So again, we don't assume that I have to continue going just because there's trig involved here. We want to try the direct substitution. So plugging 0 in would give me 7 minus cosine of 0, which is 1. So as soon as I see that this is going to be a non-zero number, I know I'm finished. There's no way that I'm producing 0 over 0 again. And then on bottom, we get 2 times 0 is 0, plus 3 times 0 is 0. That becomes this argument. And cosine of 0 is 1. 3 times 1 is 3. So we end up with 6/3, or positive 2 for our final answer. Again, just to review, just a reminder, I want to constantly remind you guys of the impact that these results have on graphs. Because I had indeterminate form to start, and then I actually found a numeric value, that means that this graph has a hole at the coordinates 0, 2. As x approaches 0, the limit does exist. We are approaching a y value of 2, but because you got indeterminate form at the beginning, that means 0 is not in the domain of this function. Therefore, this must be a hole. Okay, I've got 2 more here. Let's try this guy. All right, now this one's a fun one. So we're back to limits at infinity. So we're left wondering about these graphs. So for the first guy, I've got 5x to the 100th power. Now, you guys probably haven't seen that big of a degree. But if we just review what we know about polynomials, when we have an even degree polynomial, your arrows, your end behavior, do the same thing. So they're either both going up or both going down. In this case, because our leading coefficient is positive, we know they're both going up. So therefore, as we go to the right, we know that we are heading towards infinity. Okay? Now for the bottom guy, e to the x, right side's always going to infinity, so we get indeterminate form. So if I were to apply L'Hopital's, we would get 5 times 100, or 500, x to the 99th, over derivative of e to the x, again, is always just e to the x. Now when I do it again, now this becomes a 99th degree polynomial. So odd degrees means we do one of each. So in this case, because the leading coefficient is positive, the right side would be going up, and then the left side would be going down. But I'm really only concerned with the right side, so this is still positive infinity, and e to the x will always be going to infinity. So if you think about what's going on here, this is going to repeat itself. This cycle of indeterminate forms, it's going to keep recycling over and over and over again. The bottom is always going to be e to the x, no matter how many derivatives I take. But the top is actually going to eventually get itself down to a constant and then 0. But again, we don't want to do that all the way down to 0 because it wouldn't be necessary. We would have to keep going until one of these is not infinity. The bottom is always going to be infinity. So we would have to keep going until we reach a point where this top function's limit is no longer infinity as well. Well, if you think about polynomials, no matter where we start, eventually we get down to a constant function. So if we were to continue taking this derivative 99 more times, eventually we would get to a point where that top function is a gigantic number, okay? So that number would be made up of the 5 that was there to start. Let me get rid of this circle. The 5 was already there when I took my first derivative and multiplied by 100. Then when I take my second derivative, I would be multiplying by 99. And then the next time, 98 and 97, all the way down until I took the derivative of my linear function and multiplied by 1, and that's what would leave me with x to the 0, or a constant function. But by that point, this number is going to be absolutely gigantic. But it doesn't really matter what that number is, because on bottom, it's still just e to the x. And by the time I reach that point, when I go to take the limit of this is just a number. It's a non-zero number. Doesn't really matter how big it is. It's still just a number. And every number is smaller than the concept, the idea of infinity. Because however big this number is, infinity represents a quantity even larger than that. So just because this is going to be a giant number, it doesn't change this result. This is going to be a giant number divided by a quantity that will continue to grow without bound. So their ratio is going to eventually go to 0. Now, this is a case where we don't have to keep doing L'Hopital's, because it would take us forever to actually do this 99 times. It would be ridiculously impossible. I don't even know if Desmos can calculate that big of a number. I bet it can, but it's probably going to give me scientific notation. Now, if you're wondering how can I multiply all 100 numbers pretty quickly, in mathematics, you may have seen this in a stats class previously. There is a symbol with it's this exclamation mark that represents the concept of a factorial. It means I start with 100 and I multiply by 100 and every integer between 100 and 1 until I get that final answer. Now, it doesn't actually give me the number, because what it really is 4.6 blah, blah, blah times 10 to the 158th power. That really means it's a 4 followed by 158 other numbers. That is a gigantic quantity, but still, it doesn't matter how big it is, because the bottom will continue to grow larger while that top stays as big as it is currently. So again, another way of thinking about this is, again, going back to those growth rates. That previous problem earlier where we got into an infinite loop, we had to compare growth rates. This is just a polynomial. I don't care how big the degree is. It could be a 1/1,000,000th degree polynomial. Eventually, at some point, an exponential function will take over and be growing at a faster rate than any polynomial. Doesn't matter the degree. Doesn't matter the base of the exponential. As long as it's bigger than 1, eventually the exponential will win. So because of that, this is essentially like we have a slow-growing function over a fast-growing function, which those will always have limits at infinity approaching 0. All right, now for our last one. Another limit at infinity problem. Now this one's a little bit more complicated, but if we still think about what's going on here, we can handle it. So another limit at infinity. So for the first guy, or the numerator, that's not a function that you may offhand know what the graph looks like. So we're going to have to do a little bit of a breakdown here. So this is a composition function with a quadratic inside of a natural log. So to identify this limit, we're going to have to do it piece by piece. So if I start with, let's do it over here to the side, x squared plus 4x. If I were to take the limit as x approaches infinity of that guy, well, that is a quadratic function that opens up. So on its right side, we're definitely heading towards infinity. So if that's what the output of that function is doing, then that really controls the input of this natural log function. Or this is another way of saying what is the limit as x approaches infinity of the function natural log of x. Well, we've seen that in the past, or in this video, looking at this graph. Remember, the natural log graph is going to increase, but it does so very, very slowly. But that part doesn't matter, okay? Or at least not right now. So because of that, we know that this is the top limit is infinity. And now for the bottom, this is a cubic. Leading coefficient is positive. So we know its graph looks like this guy. So also going to infinity. So this is a good one because of the simplifications that have to occur. That's why this one's on here. So for the top guy, this is natural log of u. So remember that derivative is u prime over u. So u prime would be 2x plus 4. And then my u on bottom is x squared plus 4x. Then for the denominator's derivative, we would get 3x squared, yikes, minus 8x, and then the constant disappears. So 3x squared minus 8x. Now, again, like I told you guys earlier, once we get to this point, we don't want to leave the limits as they are right now. We want to simplify the entire expression as much as possible. So this is really like the fraction up top multiplied by the reciprocal of this guy, which really means we're going to multiply these two these two polynomials together. So when I do that, I end up with 2x plus 4 in the numerator, and then multiplying these guys, the result gives me 3x to the fourth, let's see, minus 8x cubed plus 12x cubed, so plus 4x cubed, and then minus 32x squared. So now it all combines into just a polynomial over a polynomial. So we know that this is going to give us another indeterminate result. Again, every mixture or combination of polynomials will give us some form of infinity because these guys don't approach constant values at infinity. So we got another infinity over infinity. But now the second round of L'Hopital's is a lot easier to work with because it's just straight power rules. So top turns into 2. Bottom guy, we got 12x cubed plus 12x squared minus 64x. So our constant up top is going to remain. The bottom guy is still heading towards infinity. So we end up with 0 as that final result. Now, going back to the natural log, I said the fact that this guy grows slowly doesn't come into play right now. But if we were to go back and look at this and analyze it through the idea of growth rates, this natural log function, even if I put a quadratic inside to make it grow a little faster, it's still not going to grow faster than a polynomial of a positive degree. So no matter what that degree is, it could be a first power linear function. Eventually, it will overtake that natural log. So this is another situation where it's essentially like a slow growing function over a fast growing function, which is why we end up with that 0 for our limit.